speaker of our session is Dan Christensen from the University of Western Ontario. The title of the talk is "No Set of Spaces Detects Isomorphisms in the Homotopy Category." Yeah, please take it away, Dan. Thank you.
Okay, well, thanks very much for the chance to speak. I'm very happy to be here. I'm going to be talking about some joint work with Kevin Arlen, formerly Kevin Carlson. So some of his work has appeared under both names. And I'm talking about a topic that I chose because it fits really nicely into a 20-minute slot, and there's a nice story to tell. So hopefully you'll find it enjoyable. Okay, so I'm going to start with some background. So first, let me remind you of the classic Whitehead's theorem due to J.H.C. Whitehead in 1949. So this concerns maps between pointed connected CW complexes. So we have here a map F between pointed connected CW complexes, and a CW complex is just a nice space built out of spheres glued together nicely. And then the statement is that the following two things are equivalent. The first is that the map is a pointed homotopy equivalence. So there's a pointed map going in the other direction, and the two composites are homotopic to the identity through pointed maps. So these are the isomorphisms in the homotopy category of pointed spaces. And the other condition says that you can check this by mapping spheres into the spaces. So I'm writing it in this way, but we're talking about pointed homotopy classes of maps from spheres to X, which is normally written as the homotopy groups. So you can detect homotopy equivalences by seeing if you get an isomorphism in homotopy groups. Very useful and powerful theorem. So as soon as you see this, you wonder what happens if we don't have pointed spaces anymore. So the question that arises is there some set of spaces, this script G, that has the property that when you're given a map between any connected CW complexes without base points, and the map has no other assumptions, you can determine when it's a homotopy equivalence by checking that you get a bijection when you map in from the spaces in your set. So for each S in this curly G. So you might ask this question right in your first class in homotopy theory, because in fact, your first class in algebraic topology, as soon as you've learned about homotopy, you can wonder about this result. So the history of this, actually before I say the history, so I'm going to drop the word connected. The first observation is it doesn't change things. If you have a set that works for connected CW complexes, you can just throw in a single point as an extra test space, and that set will work for not necessarily connected CW complexes. And on the other hand, if you have a set that works for not necessarily connected CW complexes, you can take the components of the spaces in that set. So it'll be convenient to drop this word. It doesn't really change the question. And in this form, Heller in 1981, so 40 years ago exactly, said that the answer to this question is no. And I want to tell you a bit about how he did this. One of the steps he did relied on a certain obvious fact, and it turns out that that fact is false. So that's why this is something interesting to talk about now. Okay, so I want to tell you the story, and so I'm going to have to give you a bunch of definitions. So the first one just abstracts away exactly the question we're talking about. It just says if we're in a general category and we have a set of objects, we say that that set jointly reflects isomorphisms if we can detect isomorphisms in the category by mapping from elements of our set of test objects. Okay, so that just gives a name to the property that we're looking for this set G of spaces. So if we work in the homotopy category of spaces, so by this I mean either take all CW complexes and take maps up to homotopy, or take all spaces but invert the weak homotopy equivalences. Either way, you get an equivalent category. And the question is, in this category, is there a set which jointly reflects isomorphisms? Okay, I'm going to repeat that definition over here. This time it has a little picture that goes with it. What the condition is saying is that for every map from a test object to Y, there should exist a unique lift through the map F, and that should imply that F's an isomorphism. Okay, second definition I need is the notion of a weak colimit. Probably in this audience, all I need to say is what's written right here. It's like a colimit, except that you only have the existence of the map, not the uniqueness. So I've illustrated it for a sequential diagram, which is the kind of diagram I'm going to deal with later. And W here is a cone on this, or a cocone on this diagram. And for every other cocone Z, there should exist a factorization, but not necessarily unique. This is important because we're working in the homotopy category of spaces, which doesn't have all colimits, but it has weak colimits. And here's the most important definition. We say that a set of objects is bounded if for every sufficiently large regular cardinal kappa. If you don't know what regular means, don't worry too much. I'll mention a bit later where it comes up. But anyway, for every large enough indexing diagram, and every diagram of that shape, there is a choice of weak colimit, which has the property that this natural map is a bijection for every one of the objects in G. This is sort of a smallness condition. So what it says is every time you have a map from one of your test objects into the weak colimit, it factors through some stage of your diagram. That's saying that this is surjective. And it's unique up to post-composing with maps in your diagram. So you might have two different factorizations that aren't the same. They may not even land on the same spot, but at some further stage in the diagram, they have to agree. So this is saying that these objects have a certain smallness with respect to long enough diagrams. Okay. This is particularly subtle because these are weak colimits. So first of all, there's not just a unique weak colimit. There can be many weak colimits. And I'm just saying that there's at least one weak colimit with this property. But it has to be the same one for every object S. Normally, if I was talking about colimits, that wouldn't be a condition because there is only one. But here, I want there to be one that works for every object S. Okay, so those are the concepts. And then Heller has a really nice representability theorem. I think it's one of the nicest ones that I'm aware of, and it encompasses many other results. It says that if you're in some category that has coproducts, weak pushouts, and contains a bounded set of objects which jointly reflects isomorphism, so I've used all these definitions on the previous slide, then if you have a contravariant set valued functor, it is representable, just in the usual sense, if and only if it does what such a representable functor would have to do, which is it sends coproducts to products, and it sends the weak pushouts in C to weak pullbacks in set. Okay. So that's a very nice theorem because it has very weak assumptions on the category C. Okay, then in the same paper where he has that theorem, he writes down a particular contravariant functor on the homotopy category of spaces that satisfies condition 2, this exactness property, but is not representable. What this functor does is it sends a connected space to the set of normal subgroups of its fundamental group. That doesn't need a base point to be well defined, because if you change base point, you change the group up to conjugation. So you get an equivalent set of normal subgroups of pi 1. On a disconnected space, you just take the product of that set for each component. So it sends coproducts to products by definition, and you can check that it sends weak pushouts to weak pullbacks. That's a little bit tricky. And it's not hard to see that it's not representable just by a sort of cardinality argument. Okay, so at this point, once you've seen this example, you realize that the category spaces must fail some of the hypotheses here, at least one of the hypotheses. Is there a question? I just heard something. No? Okay. So the category of spaces, the homotopy category does have coproducts. It does have weak pushouts. So it must be one of these two bolded properties that fails. So this is where Heller said, obviously, every set of CW complexes is bounded in the homotopy category of spaces. And then he said, therefore, there must not exist a set of objects which jointly reflects isomorphism. So I read this paper a long time ago, and I believed this claim. It is completely obvious. So what the argument is a standard argument. If you have a set of CW complexes, you look at the largest number of cells that any one of them contains, and you choose a regular cardinal larger than that for your boundedness cardinal. And if you've got a diagram indexed by that cardinal, you just take the usual Milnor telescope where you sort of glue on cylinders at each stage. And then it's really easy to check that any map into the colimit of that diagram does factor through a stage, and it has exactly the condition. The condition, this equation right here does hold for that construction. Unfortunately, that construction doesn't give you a weak colimit in general. That's the part that's supposed to be easy is the part that fails. You get the sort of boundedness, but you don't get the weak colimit property. Okay, so this claim is false, and that's the first theorem that Kevin and I proved. And you don't need any exotic CW complexes. If you just take the collection of spheres, they don't form a bounded set in the homotopy category of spaces. So once you realize that, you then realize that this question that I asked at the beginning is now an open question, because the argument that is outlined on this slide, this third step, and notice how nice these boxes are. See, I've improved my template since I sent it to Martin. This third claim here is not true, so the argument doesn't hold anymore. And we don't really know whether this conclusion is true. Okay, but then our second result is that Heller was right. There does not exist a set of spaces that jointly reflects isomorphism in the homotopy category. Okay, and I'll just mention that once you have that second result, it follows that the same problem happens in many other categories. So for example, in the category of quasi-categories, the same thing is true, the homotopy category. So in contrast, if you're not working in the homotopy category, if in fact you just go one dimension higher, so if you work in the two category of spaces, continuous maps, and homotopy classes of homotopies, then the spheres do jointly reflect isomorphisms. So it's only when you've truncated fully down to the homotopy category that this problem occurs. Okay, so between these two theorems, it turns out the theorem one is the really hard one, at least for us to prove. But once you realize, I didn't mean to click the page there. Once you realize that it's not true and you need a new argument here, it's actually not so hard to prove theorem two. So for theorem one, I'm just going to very briefly say a bit about it because it's quite technical and it certainly won't fit in this talk. So this is just a rephrasing of it, but I've just unfolded the definition of what it means to not be a bounded set. So this means no matter how big a regular cardinal you pick, there is some diagram of that shape which has no weak colimit that has this sort of boundedness condition holding for all of the spheres. Okay, so the first step that we do is we show that if you show that this condition fails in the homotopy category of groupoids, so that's the category where the objects are groupoids and the maps are functors up to natural isomorphism, then it will fail in the category spaces. So it's sufficient to work with groupoids. So what we do is for any kappa, we have to come up with this diagram, and we take a very natural diagram. So we think of kappa as the set of all the ordinals smaller than it, and the diagram sends an ordinal to the free group on that many generators, thought of as a groupoid with one object. And the morphisms in the diagram are just the natural inclusion sending generators to themselves. So the trickiness is to show that you don't get any possible weak colimit that satisfies this condition. And for that, we basically have to solve some version of the word problem for groupoids that arise in this question. We have to construct a cone on that diagram, or I should say a co-cone on that diagram that's sufficiently pathological that you can't possibly find a weak colimit that satisfies this and that factors our co-cone. And that involves basically working with the word problem in a very complicated groupoid. Sayre's book on trees has a theory of graphs of groups that we use, and Higgins has extended that to basically give a lot of results about groupoids and fundamental groupoids of things that you construct in that way. So we have to rely on these results, and that's the trickiest part of the argument. Okay, so what I'd like to do is spend the rest of the time talking about the second theorem, which is something that can be explained in well, maybe in the remaining time, at least a high-level sketch. So this is the statement that there is no set of spaces, or really CW complexes, that jointly reflects isomorphisms in the homotopy category. All right, so here's how this goes. It's very explicit. So suppose you start with a set of spaces. For any set of spaces, I have to come up with a map that this set of spaces views as an isomorphism in the homotopy category, but which isn't an isomorphism. Okay. So given the set of spaces that you provide, I take a regular cardinal larger than all of the homotopy groups of all of those spaces. And I'm going to work with the following group. So I'm taking the symmetric group on the set alpha. So alpha is this really large cardinal. I take all the bijections of that cardinal with itself. But this C is supposed to mean something like compact support. And what I mean precisely is that if you look at the subset of alpha of all the points that are not fixed by an element sigma, that has to have cardinality less than alpha. So it's permutations that have support that's strictly less than alpha in cardinality. And then I define a homomorphism, S, from this group to itself. And it's basically conjugation by the predecessor map. So sigma here is one of these compactly supported permutations. So S sigma is a new permutation, which takes as input an ordinal gamma, which is less than alpha. If gamma has a predecessor, gamma prime, then I just apply my permutation to gamma prime and then take the successor. So I start with gamma, I take its predecessor, apply sigma, and then take the successor. So I'm conjugating by this predecessor map, except that the predecessor map's not defined everywhere. So if I've got a limit ordinal that's not a successor of anything, then I just send it to itself. And since I have this +1 here, this case never hits a limit ordinal, so I can sort of treat the limit ordinals and the successor ordinals completely separately. And it's not hard to see that this is a bijection, that it does have compact support, because if gamma is fixed, well, I guess if gamma prime is fixed, then this will send gamma to gamma. So everything that's fixed by sigma, its successor is fixed by S of sigma. And you can also check that it's a homomorphism. It's just a simple calculation. So this is a group homomorphism between these two large groups. So that means I can look at the induced map on classifying spaces. So B sigma alpha C is the space which has pi1 equal to that group, and it's connected and has all higher homotopy groups trivial. So there's an induced map on spaces. And that's the map that I claim will give the example here. Okay, so here I've just written it down again. That's the map. And here's a calculation we can do. So in the category of unpointed spaces, if I want to look at maps between classifying spaces, those are the same as group homomorphisms modulo conjugation by elements of the codomain. So it follows that if we have a map here that is a homotopy equivalence, it has a homotopy inverse, which will be induced by some map from G to H. And the composites will be conjugate to the identity maps. But something conjugate to an isomorphism is an isomorphism. And that would mean that our homomorphism is in fact an isomorphism. If it has an inverse that gives a composite that's an isomorphism, then it had to be an isomorphism. So this map S is not an isomorphism though, because it's not surjective. it produces permutations that always preserve limit ordinals, and there are certainly permutations that don't do that. So it's not an isomorphism, so this map is not a homotopy equivalence. Okay, so that's good. So now the claim is that when we test this map using things in our given set, it will produce a bijection. And in order to check this, it's enough to check it for classifying spaces of groups whose cardinality is less than alpha. That's because we're mapping into a one type, and any map from a space to a one type will factor through the one truncation of the space. Also, if the space is disconnected, it's enough to check it on the components, so we can assume it's connected. And the one truncation of a connected space is just the classifying space of its pi1. And we chose this alpha so that all of the pi1s of these S's have cardinality less than alpha. So if I check it for every BG, where G is a group of cardinality less than alpha, then it'll be true for all the spaces S that I started with. And for such a space BG, I get an even stronger claim. Not only is this map a bijection, it's actually the identity map. That's what I claim. Okay, this is the last slide with content, and I'm just a bit over time, so let me just very quickly do this. So I claim that that's the identity map. And I'll just show you the permutation that does this. So I define this permutation tau, which is roughly like the predecessor map. It's a predecessor map up to a certain point beta for successors, when gamma is a successor, up to a certain point beta. For the limit ordinals down there, it has to bump them somewhere else. So it sends them to beta plus what they were. So it kind of stores them up above beta. It makes room for them by moving things between beta and 2 beta all up one. And stuff above 2 beta, it just leaves alone. So this is roughly the predecessor map with a little bit of bookkeeping that I can do because I have this beta. And this beta, this is where I use the fact that my cardinal alpha is regular. I can use the fact that the supports of all the values of a homomorphism from a group whose cardinality is less than alpha have support less than some common beta. So then because of that, you can actually check that this function S I defined actually just is conjugation with tau for sigmas that only move things up to beta. And that's really the key, because in here we're looking at things up to conjugation by elements of the codomain. So when I apply S to something, I'm getting actually something that's equal because it's just conjugated by something in the codomain. So I've gone through that a little bit quickly, but that's because I'm over time. And so that proves that claim. So that particular map does appear to be an equivalence, in fact, the identity from the point of view of the test spaces, but it is not actually a homotopy equivalence. Okay, so in this slide, I'll just show some references to the original paper of Heller and the work of Higgins and Sayre that was used for Theorem 1. These slides are already on my webpage. I will also put them in the forum a little bit after the talk's over. Okay, thanks very much.
Thank you. Thank you very much for the great talk, Daniel. Are there any questions or comments?
Maybe just a comment. I'm trying to understand Dan.
Yep.
Okay. Nice talk.
Thanks.
I'm trying to understand the argument. So somehow your map S is really a conjugation in a larger group, right? It's a conjugation in the group of all permutation of alpha.
It's not even quite true there, but it's true. The value of what S does for any particular element can be described by a conjugation, but the tau depends on the element.
I agree. I agree with that. Yeah. Yeah. For this last argument, you're sort of showing that for a smaller group, although this transformation is not a conjugation in sigma alpha C, it becomes a conjugation for smaller groups.
Exactly, yeah.
Okay. Okay, I'm going to think about that. That's an interesting construction.
Yeah, and I should say that, you know, the case of countable, like showing that spheres don't detect all equivalences, you do a countable version of this argument, and that was known. The trickiness was trying to extend it to larger cardinals and do the sort of bookkeeping that's needed here to make this work.
So these counterexamples are all about non-simply connected spaces, right?
Mm-hmm.
So if you look at pointed simply connected space, then of course there is no such, that's the set of spheres. I mean, yeah. If you take the connected, even the connected, pointed connected spaces, right? That was your...
Well, with pointedness, there's no problem. It's only with unpointedness that there's an issue. So maybe you're wondering about unpointed, simply connected spaces, which is a good question. I don't know the answer.
I'm not sure. Okay.
Yeah, it's a good question. I'll think about that.
Thank you.
Oh, thanks for the question.
And sorry, Nan, perhaps you said this already, but for the case of spheres, is it easy to understand the concrete map, which is not a homotopy equivalent, and induces isomorphisms in all these books, in all these sets?
Well, I mean, it's essentially the same sort of thing. You just choose alpha to be, I think you can choose alpha to be omega or something like that.
Okay, so it's part of this general construction, but there is not more a really concrete description that you say is these two spaces, they look like this.
No, but it's the finitely supported permutations of the infinite symmetric group. I think that's what it turns out to be in that case.
Okay, thank you. Beautiful result. Congratulations.
Are there any other questions or comments? Well, if not, let's thank Dan again.